morning. I am trying to wrap up 6.1 notes with this video. But in this particular section, our job is to look for what sample size is needed. This is pretty traditional. To build a confidence interval, you usually want to decide up front how much error you're willing to live with. And then that kind of helps you build backwards on the sample size you need to investigate your population. So our situation in number 3 is that we have a doctor at a local hospital interested in estimating the birth weight of infants. How large of a sample must she select in order to be 98% confident that the true mean is within 2 ounces of the sample mean? And we are going to start with a standard deviation of 8 ounces. So that's half a pound, right, if you want to think of it that way. So the error that they're giving us to live with is 2. And the confidence level was 0.98. So we do have a little bit of work to do because we have to find our z. It's not one of our popular guys. And so we need to look up, this is our question mark, we need to look up an area of 0.01. Why? Because that's half of what was left from 100%. So if I look up an area of 0.01, and some of these you look up so much you end up memorizing, which is kind of nerdy. But so get on our table and look up an area of 0.01, and the closest we can get is negative 2.33. But remember, when we record the critical value, we just use the positive version. Okay, now we're going to use the formula for area. The formula, not area, that's geometry class, just kidding. We're going to use the formula for error. And error is the critical value times the standard deviation divided by the square root of n. N happens to be what we're solving for here, so we're going to hope that we have everybody else. And if not, we can't finish our problem. How's that for fun? So the error was 2. The critical value was 2.33. The standard deviation was given to us as 8 ounces. And maybe that's just a known fact for babies. I don't really know. Divide by the square root of n. So we would multiply both sides by the square root of n so that it's no longer in the denominator. And we would have 2.33 times that 8. And then we'd have to come back and divide by 2 to get the square root of n by itself. Now, we can do that math. The square root of n ends up being worth how much? 9.52. And in order to undo square rooting, we do have to come back and square. So the n ends up being 86.86. Now, you can't sample a partial baby. That's kind of gross and leads into really bad jokes. So no matter what this number is, we're always going to round it up. In this case, it would naturally round up. But even if it was only 86.1, we would still round up to 87. So our sample size that we need for number 3 then is 87 babies need to be sampled in order to stay within that error. So let's try that one more time. In number 4, we have an insurance company trying to do what? Determine the estimated number of sick days a full-time worker uses in a year. A previous study shows us that a standard deviation was 2.5 days. How large of a sample must be selected for the company to be 99% confident that the true mean differs from the sample mean by no more than 1 day? So what information were you given in this? And maybe that's why I like these problems. They're like puzzles. But you were given a standard deviation of 2.5. How large is what you're looking for? So you're looking for n. Your confidence level is 0.99. And your error, we don't want to be more than a day off in our values for our confidence interval. So the question is the 0.99 one of the famous guys? So we go to our table, we look at the critical values, and 0.99 is one of the popular dudes. So our critical value for z is not one that we need to calculate. We can steal it from the table. That's so awesome. Less work for us. Excuse the sniffles. The oak trees are killing me right now. Alright, take your error equation. Error is critical value for z times standard deviation divided by the square root of n. Plug in everything you know and solve for what you know. So the critical value was 2.575 times the standard deviation divided by the square root of n. So just like in the last problem, you will need to solve for n by multiplying both sides by the square root of n. And since there was a 1 on the other side, there's no need to come back and do division. So 2.575 times 2.5 gives us 6.4375. And we know to undo the square root, we're going to have to square this number. So there's our n value. And n is 41.44. Now, like I said in the previous example, you always want to round up. So they would need to sample a minimum of 42 employees so that they could ensure that they were 99% confident that the true mean would differ no more than a day. Awesome, I'm done with you, bye.